Hello and welcome back. This is Advent of Code Day 8. This is not quite a live solution. I already solved this last night and posted some code in the Reddit thread. But I thought it would be good to just go through the problem because I think that this is a really great problem for APL. It shows one of APL's strengths, which is working with multi-dimensional arrays. So yeah, we'll look at that. In particular, I want to look at the rank operator and sort of how you go about working with these large arrays without having to split it into smaller arrays and using the each operator and that sort of thing. So let's get right into it. So I have my puzzle input, quad inget po8.text. I get a long string of numbers. Now, so I don't know about you viewers, but for my input, I get this one character on the end, which is sort of, if I just do for each execute, I get an error. That's because the last token here, if I do the neg1 take enclose, it's like a new line character or something like that. But when I look at the file, I don't have, I can't find any new line characters or anything. So, I've tried deleting the file and re-downloading it. Yeah, I don't really know what's going on there. So what I'm going to do is I'm just going to do the neg1 drop, and that will give us an even 15,000, and then we can do for each execute. That will give us a numeric array, and yeah, we can sum it, we can do whatever. Okay, so the problem calls for basically, we are supposed to split this numeric array into a rank 3 array. So we'll have 100, well, we'll figure out how many layers there are, but so we're dealing with a bunch of layers, each of which is 25 pixels wide and 6 pixels tall. So in the language of APL in row major order, this will be 6 rows and 25 elements wide. So yeah, so 6 by 25 is 150, as APL will tell you. And so if we take, we'll just call this P for right now. If we take length P divided by 150, we get 100. So we know that we have 100 layers. And originally, I wrote some code to figure out what the number of layers is for each input because I thought that it couldn't be, it wasn't going to be a constant. But looking at other people's solutions, it looks like everyone gets 100 layers. So we can actually just do, we can just reshape this into 100 layers, 6 rows, 25 columns each. And we can assign that to P. And then if we look at P, yeah, so it's getting cut off here, but basically you can see that it's rendering each layer 6 rows, 25 columns. And if we look at the shape of P, yeah, 100, 6, 25. So as much as possible, this problem, just to try and like really keep with the array-oriented nature of APL, we are going to keep P in the shape as much as possible. Meaning, so in previous days, I've done a lot of splitting and mixing and sort of working on different nested lists. For this problem, I want to try and just keep the array flat and just keep it in its original configuration as much as possible. So, yeah, and we can, yeah, well, so that's P. So what are we doing? So the elves would like you to find the layer that contains the fewest 0 digits. Okay. So there's a couple ways to do this, but we can just say 0 equals p, and this will of course generalize to the whole shape. So this will give us a 1 in the case where it's a 0 in p and 0 otherwise. And so with that, we can sum. Now, the interesting thing here is this is plus reduce, and reduce by default will reduce along the last axis. So in a rank 3 array, it'll reduce along the last one. So if we do sum of 0 equals p, we get this. And so the interesting thing, if you look at the shape of this, this is 106, right? And the shape of p is 106.25. So we basically reduced along the last axis, turned that into a single element, and then gotten rid of that axis. So what do these numbers represent? Well, so for each row is now a layer, right? And each column is a row within that layer. So if we want to get the count of zeros for each layer, then we just have to sum again along the last axis. And get this. And the length of this one is going to be 100, right? So we summed against the last axis twice, and now we're left with the sum of zeros in each layer. And the problem asks us to find the layer with the fewest zeros. So what we can do is we can use the index of operator, and well, I mean, if we just do min scan like this, it'll find us the minimum. So the layer with the least zeros has 7 of them. And we can construct a train that says index of. So what this basically says is take the right argument and then find the index of the minimum within that argument. It'll give us index 12. And with that index, we can then use that to index back into P, like so. And so this is the layer with the fewest zeros. You know, we said that this should contain 7 zeros, and just sort of visually looking at it, I think, yeah, there's 7 here. Okay, great. So that's the layer. And by the way, so you'll notice that when we select like this, because the array is flat and we're not dealing with nested arrays, you don't have to disclose. So you don't have to worry about like enclose, disclose, all the stuff that we were dealing with in previous days. When the array is flat like this, it's just all of this works like you'd expect it to, and it's very smooth. On that layer, what is the number of 1 digits multiplied by the number of 2 digits? Fair enough. So there are a couple different ways to do this, which is why I like APL, by the way, because you have this kind of flexibility. But what I ended up doing was, okay, so we can sort of solve this the same way that we did with zeros. We can say 1 equals, for example. That'll give us, you know, all this stuff, and then we can sum it twice to get 21. And if we first ravel P, so we just put it into a long list with, this will be 150 elements, then we can just do 1 equals sum, and that'll give us the number of 1s. Now, so I'm going to use a trick that I don't think that we've used in previous videos, but it's something that you should keep in your back pocket, which is the Cartesian product. This jot period function. So what this will do is for each element in the list on the left, it will apply the function to the argument on, well, the corresponding argument on the right. And you'll get a matrix, actually. And the shape of this matrix will be, the rows will be the number of elements on the left, and the number of columns will be the number of elements on the right for this. So, you know, we can do this with 0 as well if we want to. We get a three-row matrix, but because we're only counting 1s and 2s, we just do this. And then if we want to add these up, we can sum it along the rows, and that'll give us the count of 1s and the count of 2s. And then we can just multiply it, and that'll give us the answer. Another thing that you could do, if we go back to our layer here, you could use the key operator to count. But if we're doing that, then well, we want to take out the zeros, so we'll do 0 without 0, like this. Oh, rank error. So we'll ravel it first. So this is the list with the zeros taken out. And then if we use the key operator, which I'm not sure if I've used this in previous videos for last night or previously. But basically what this does is you can do, let's say, like, show you what it looks like. Yeah, better. What this does is on the left, basically the key operator will group all the elements in the list on its right. And so on the left, you'll have the actual value of those elements. Now on the right, you'll have a list of the indices in which that element appears. So this is useful for any sort of like grouping, counting, anything like that. And so what we can do, if we take alpha length w, we'll get the element on the left, and the count of that element in the array on the right. And then if we just take the rightmost element, we can just do length w like so. And that'll just give us the elements on the right, and then we can do multiply reduce to get the same answer. And then if you want to be extra fancy, this could actually be written as right tech jots length, like so. So you can use the key operator. So Cartesian product, key operator, there's different ways of doing this. But yeah, that's our answer for that. Yeah, 2562. So part 2 is a little bit different. Ready to decode the image. The image is rendered by stacking the layers. Right. So the idea is basically you're going down through each layer, and 2 is transparent, so you don't care about it, but you're basically taking the first occurrence of 0 or 1 that you come across. So let's look at P again. So one way that we could solve this is by using reduce first. So reduce first is this slash with a little line through it. Rather than the normal reduce, which will work on the last axis, reduce first works along the first. So if we look at the shape of P, we have 100, 6, 25, right? And if we say, plus reduce P, and then we look at the shape of that, we have 106. But if we say reduce last, then we get 625. So reduce first, this operator here, basically has the effect that we want of like going down through the different layers. So what I've done here is I've just added down through the layers. This is like just smushing all the layers together, adding them up, and these are the totals for the different positions. So what we'll do is we'll write a function, and the function will basically be actually reduce works right to left. So what we'll need to do is flip P along its first axis. That's what this one means, reverse first. And it's kind of, it kind of makes sense because it has a little horizontal line through it, so you can think of it as like flipping the whole thing around the horizontal axis. Yeah, so you can see here 22122 whatever is actually the first layer that appeared before. So we're just reversing it, and then we'll do reduce first, and then the function that we want is like alpha. If alpha equals 2, then, or rather, if w equals 2, then alpha. Otherwise, omega. So this is just basically saying, you know, if you're going down through the different layers and you encounter a transparent pixel, then just use the pixel that you already have. Otherwise, yeah, use the pixel that you're reducing into. And then we'll be doing this for each, because this doesn't, I'm just comparing a single element here. I need to do it for each element in the layer as we descend through. So it'll look like this. And yeah, you can see basically we filtered out all the 2's, and there's some sort of shape there. And then in order to get the shape, we can just take space, hash, and index into it using this array. Oh, right. So I am in, so by default, of course, APL uses an index origin of 1, so we'll just add 1 here. And that's our answer, ZFLBY. So this is the solution that I originally had, and it's fine, but I wanted to come up with something a little more area-oriented. So in order to do that, first I'm going to talk about the rank operator. So we haven't gotten an opportunity to use this, but we have used the each operator quite a bit. So let's imagine that we had a 3-3 row I9 matrix. We'll just call this M. So this is M, pretty standard, and you know, we can do standard operations on it. We can add 3 to it. If you wanted to do something like, let's say you wanted to do, like, for whatever reason you wanted to prepend 1 to each element in the matrix. Well, if you do that this way, it'll kind of expand, and you know, you're not getting the effect that you want. But if you do if you use the each operator like this, now we're talking. So what each does is it will go through each element on its right, and actually each element on its left, and it'll combine them together. And the result that you get is always going to be the same shape of the result on the right. So the shape of this 3-3 is the same as the shape of M 3-3, and it does this by enclosing or creating a nested list where necessary to maintain that shape. There's a different way to do this, and so I'm going to introduce to you the rank operator. So let's just say that we're doing this rank 0 M. Aha, we get this. Now, I haven't explained rank yet, but this sort of looks, I mean, we have the same values here. 1, 1, 1, 2, 1, 3, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and And actually, if I mix this output from each, I get the same thing. So what's going on here? Well, the rank operator will basically modify the function to work on the different elements in the shape of its left and right arguments. So what kind of shapes do we have? Well, let's just take like the shape of, you know, just a scalar like 4. You don't get anything. So this is, we call this the rank 0, right? So if, for example, we had a list of 2, 3, 4, 5, well, this has rank 1. So row is how you get rank. And if we wanted to operate on each one of these elements individually, we would say that we want to apply a function rank 0. So, I mean, plus isn't a great example here because it'll work anyway, but the prepend that I was talking about previously, so like if we wanted to prepend 10 and we say rank 0, aha, right? So now this has basically been extended and we get this functionality. What if, let's say, so we have m, let's say that I wanted to add the list 1, 2, 3 to it. And what I'd like to happen is for each row in m, I want to add 1, 2, 3. Well, if I just do it like this, I get this rank error, mismatched left and right argument ranks. But if I use the rank operator and I assign it to rank 1, which remember rank 1 is basically like a single list, you can think of it as basically being the rows in a two-dimensional matrix. Now it works. So what rank 1 is saying is for this whole list, apply it to each list in matrix M. And we get, 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 3 is 6. That's fine. But then as you move down, 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9, etc., etc. Right? In addition, you can actually, rank will take a list of 2 arguments as well. And if you specify it 2 arguments, it's telling you how to consider the rank for each of its left and right arguments. So let's imagine that we had, before I get into this, let's say, let's just look at M again. So it's a 3x3 matrix. And let's say that I wanted to sort of, for the list 1, 2, 3, I want to add 1 to the first row, 2 to the second row, and 3 to the third row. Well, one way that you could do this is you can just append 1, 2, 3 to M, like so. And then you could, actually it doesn't even work. That doesn't give you what you want. Because you want to add, yeah, I don't know how you do this without the rank operator, but let's just go with the example. So you want to add 1 to the first row, 2 to the second row, 3 to the third row. Well, what you can do is you can say, okay, rank 0, 1. And what this says is basically for our right argument, M, consider each row. But for our left arguments, this list 1, 2, 3, consider each individual element. That's what rank 0 means. So 1, 2, and 3. And if we do this, we get, and here's M for comparison. So we added 1 to 1, 2, 3 to get 2, 3, 4. We added 2 to 4, 5, 6 to get 6, 7, 8. And we added 3 to get 10, 11, 12. So the rank operator allows you to basically get this kind of looping functionality that you might miss from other languages. And it can allow you to come up with some very concise expressions. The other thing that I'll say about the rank operator is actually it's extremely similar to the each operator that we've been using all along. So what did I have previously? So I had like 10 each M, like so, right? And if instead we say 10 append rank 0 M, now I get this. So these two shapes are very similar, right? And the interesting thing is that if you mix this result with each, you get the same result as from the rank operator. And if you add an enclose when you're working with the rank operator, you get the same result as each. So basically each is rank 0, along with an enclose, and it'll use the enclose if it needs to keep the argument, keep the result in the same shape as its right argument. The rank operator doesn't have that restriction, so it'll return you results in whatever shape makes sense for what you're trying to do. But these two operators are like very closely connected. It's kind of interesting. So when you're trying to keep objects in a like a big array like P here, our puzzle input, we're going to be using the rank operator, whereas previously we might have been using each. And the reason is that the rank operator will never nest the array. It'll always keep it flat. And then we don't have to worry about enclosing, disclosing, this other stuff. Okay, so think about our problem. We want to go down through the different rows, or the different layers, and we basically, 2 we don't care about because it's just some transparent pixel. But what we really want is, as we go down, we want the first occurrence of either 0 or 1. And we want to keep that. So how do we operate sort of for each, if you imagine the layers, stacked up on top of each other, how do we move down through the layers for each element in the same relative position? Well, we can transpose P. Let me get this. So transpose, if we look at M and we transpose it, I mean, this sort of makes sense, right? This is transpose that you might remember from, I don't know, linear algebra or whatever. You're just sort of flipping elements about its diagonal axis. What transpose actually does, though, is it reverses the shape of its argument. So if we look at the shape of P, it's 100 layers, 6 rows, 25 columns. And if we transpose it, now it's a 25 layer, 6 row, 100 column array. And now that, so basically each one of these rows here in the transposed representation is, if we consider them individually, this is what we want to be operating on. Each one of these rows represents, for the same relative position in the layer, a descent through the layer. So how do we operate on the row? Well, we can use the rank operator and operate on this rank 1. Rank 1 is each row, right? So let's do that. So we have transpose P. And then we know that we're going to be doing rank 1 something. And what are we going to be doing? Well, so think about this. We want the index of 0 or 1, right? So index, and we'll flip this like so. And this will basically tell us for each row where the first occurrence of 0 or 1 is, right? So if we look at like row 3 here, we can see that 0 first occurs at basically the first element, then 1 first occurs at the third element, remembering that we're using 1-based indexing here because this is the default. And we can see that for the third row, that is indeed the case. So 0 occurs first, and then 1 occurs third. So what we could do now is we can reduce along the last axis, because let's look at the shape of this, 25, 6, 2. So in order to get our result, which we want to be in shape 625, we're going to have to take care of this 2 here, and we do that via reduction. And so we could reduce like, let's say we reduce with greater than. And so think about it. We're trying to figure out whether 0 or 1 came first. And so we can use the greater than operator as a proxy for that. So basically, if the first number is greater than this one, the second number, then we'll report 1, which makes sense because 1 came first. But if the second number is greater than the first number, meaning that 0 came first, then that'll be false, and we'll get 0. So this is kind of just a clever way to put these two numbers together. Hopefully this is making sense. And then if we transpose that back into its previous shape, we get this. And we can index into it. Just as before, we'll have to add 1. And we get the answer. So this is one of the ways in which the rank operator can really make your life easier, where instead of having to split the matrix into like a nested list, like for example, here's P, right? And I could do something like, if I split P, what's the shape of this? 106. And then if I concatenate like so, yeah. So the shape of this is 100 layers, and then the shape of the first element of P is going to be 150. So you could do something like this, where instead of keeping everything in like a big flat matrix, you just consider each layer sort of individually. And then when you get to the end, you'll do like a 6-row 25 reshape. Right. But you have to, the performance is going to be worse. You have a lot of pointers to new lists. You're going to have to enclose and disclose stuff all the time. So, keeping things in a single large array and then using these array-based techniques with the rank operator, for instance, is a really nice way to do things and feels more array-like to me anyway. Yeah. So that is the solution for day 8. So as the days go on and you're trying out APL, maybe try and keep things in larger flat arrays, because your performance is going to be much better because you can do more things in parallel, and your memory management is all contiguous, and it just feels more array based, which is kind of nice. So anyway, hopefully this was informative. Do let me know if you have any other questions, and thanks for watching.